So, thank you very much, Matteo. It's a great pleasure to be here. This is my first time actually in Padua, and I think the micro is a little bit too strong, like this. So, although here are a lot of colleagues which I know for more than 25 years, I think it's really my first time, and it's a great pleasure to see them all here. But the aim of this talk is that these colleagues should be rather bored. It's really a question, so I want to address the non-experts here in the field and to explain a little bit the study of rational points of algebraic varieties. So this is the main thing which one does in arithmetic geometry. And so the idea is to explain the ingredients of the Birch-Swinnerton-Dyer conjecture, which is one of the 7 millennium problems. And so there is no way that we can solve this question at the moment, but there has been some recent progress. And at the very, very end, so in the last 2 minutes, I will explain this progress. Yeah? So this is the outline. Let me start with a very general introduction or motivation. So we study solutions of polynomial equations, and so this is as follows. We want to study this set. So this is the set of all points, x1 up to xn, rational, such that they solve polynomials like this. Yeah, this is much better. So the PIs here are polynomials with rational coefficients in n variables. Yeah, like this. So I equals 1 up to m, say. Yeah, and we want to say, so the first naive question one could have is somehow, are there any solutions? And if there are solutions, are there only finitely many or infinitely many? Can one say something about the qualitative behavior of these solutions? Is the fact that there are solutions connected with some interesting arithmetic invariants which you can otherwise attach to these varieties? This is the kind of question we want to ask. So, so the question here is, for example, the most naive question is this finite or infinite? And to see a little bit what's happening, let's consider very easy cases here. And first of all, let me say that we can attach a dimension to such a situation. So the dimension of x, this is essentially n minus m, at least if the polynomials are sufficiently general. Yeah, so there's a dimension, and to see what are the easy cases, what are the more difficult cases, we can somehow start looking at small dimensions and see what's happening. So let's first consider at dimension x equals 0. This is already interesting. So then this boils down. So this amounts to solutions of essentially one polynomial equation. So px in one variable. Px equals 0. So p is a rational polynomial in one variable. Yeah, and everybody knows how this works. So we can write p of x as a product, I equals 1 up to to n, say x minus alpha I. The alpha I are some complex numbers. Yeah, these are the zeros of this polynomial. And then x of q in this case, this is just the set of alpha i's such that alpha I is a rational number. Yeah? So there are finitely many in this case. This is clear. And we have a good overview over these solutions. But this doesn't mean that these solutions are easy to find or anything. And one important thing in number theory is if you look at this baby case, then you already see that it is important not only to consider rational solutions, even if in the end you're only interested in rational solutions, but it's important to consider the field generated by this root. Yeah, so you consider somehow K, which is the field generated by the roots of this polynomial. Yeah? And this is a finite field extension of Q. And in good cases, or you have the Galois group acting. So this is Galois theory. Yeah? That's a Galois group of this extension. And the fact that alpha I is rational or not, you can say as follows. So xq is then the set of alpha I such that the alpha I is fixed by all elements in the Galois group. Yeah? This is another way to express this fact that the solution is rational. You don't need to understand this. This is only a hint that somehow field extensions show up very natural in this business. Okay, this is the case dimension 0. Oops. It's clear. This happens. Okay. So let's look at the next step. What happens for dimension 1? Okay, let me first remind you that in dimension 1, you can, for technical reasons, I make this remark only, so better one uses homogeneous polynomials, which means you work in projective space. But this is only a technical remark, so we want to have projective or smooth projective varieties. And then if you look at the solutions, you can ignore this. This is a technical point. If you look at the solutions in the field C, then this is really a Riemann surface. So, and we know that the Riemann surfaces, the compact smooth Riemann surfaces, can be classified according to their genus. So there's the genus. There are many ways to define the genus. I don't want to do it. I just draw pictures. So we have genus 0, genus G. So this is genus 0. This is the sphere. Then we have genus 1, which is a donut. And then we have genus 2. And so on, getting more and more holes here in the donut. So this is a topological classification, and this you can also do algebraically. And in a certain sense, it turns out that this topological classification is also important for the study of the solutions of polynomial equations. And this is, in fact, something phenomenon which you have always in studying solutions of these equations, the topology of the variety and certain cohomology of it plays an essential role. Yeah, I cannot explain this at all, but you see this as a hint already what comes next. So we study now the case dimension x equals to 1. Yeah, and we have these cases according to the genus, and it turns out that the things behave quite differently depending on this genus. So genus x equals 0, then we know the following. So if the rational solutions are not empty, so if there is a solution at all, then this implies already that x is isomorphic as an algebraic variety to the projective space. Yeah, so the projective space, c-valued points, this is really this sphere. Yeah. So in the projective space, you don't need to know very much about the projective space. The projective space, the rational points can be written down easily. Yeah, so this is all projective coordinates, x1, yeah, such that both entries are in Q. And the only condition is you have here is that not both of them are 0. x0, x1 is not equal to 0, 0. And if you look at this, you have in here, for example, the space of all x0 dot 0. And x0 is an invertible element in the rationals. Yeah? And this we write as gm of q. Yeah? And this is, of course, the same as q star. Yeah? So there are infinitely many rational points here. And we can easily write them down. Yeah, so this case is very easy. Either the thing is empty, and if not, then it's infinite, and we have a very good control. Yeah, that I write it this way, this has an important reason which will come, which I explain later. So this is infinite. Yes, please. No. Yes, because I want to have gm here, not the affine line. You will see why. Wait a little bit. So yeah, it's good that even the algebraic geometry colleagues, you will see why. So let's look at other cases. This looks very promising, and somehow one gets a feeling that this is an easy business, but this is very much misleading. So the next step is genus x equals 1, and this will be the next section. So let's consider genus x bigger than 2. And here, this is extremely complicated, and there's a theorem of Falting's saying x of q is always finite. Yeah, this uses extremely difficult methods. I cannot go into this here. And this is a theorem of 1983. This is old now, but it's already extremely difficult. And settles this case. And in a certain sense, one thinks maybe things become more and more difficult the higher the genus is. but it turns out that the case genus X equal 1 is even more difficult than the higher genus case here. Yeah? So let me somehow close this motivation section with X has higher dimension. There we don't know very much. We have a conjecture. Conjecture by Birch-Lang. And this says xq is finite if and only if X does not contain any group variety. Yeah? So a group variety, this is somehow given by polynomial equations together with a group law, such that the group law is also given by algebraic equations. This is like Lie groups, not only in the algebraic geometry setting. And now you see why I wrote the P1 thing in such a strange way, because this is the easiest group variety you have, the multiplicative group, and this sits here inside. And in fact, you don't, if you look a little bit at this, then it turns out that the only thing you have to require here, the variety does not contain a GM or an abelian variety. But this is only for the experts. Okay, there's not much known about this conjecture and this generality, but again, Faltings came to the rescue and proved something. So Faltings proved that Lang's conjecture is true if X is an abelian variety. And this is the projective group variety. Yeah? Then one knows this. For subgroups, sorry, for subvarieties, if X is a subvariety, this one should say better. Subvariety of an abelian variety which does not contain a sub-abelian variety. Okay. I think that's right. Good. This is an overview. And now we have one case to study, and this comes next. So we study now elliptic curves. So, and these are, so genus X equals 1, plus there is some specified rational point on X. So X of C is now a Riemann surface of dimension of genus 1. And this means there exists up to scalar exactly one holomorphic differential form omega on X. This is one definition of the genus, in fact. This is this dimension of the space of holomorphic differential forms. Yeah, so because it has genus 1, there's only one up to to scalars. And also, one can look at the singular cohomology of X, yeah, values in Z, or the singular homology, I should say. So this has two independent elements, alpha, beta. And this is quite easy to see. So again, the topology comes somehow in, yeah? So the point here is, if you look at this donut, make it a little bit bigger. So there's no colored chalk now. Okay, you have two paths. There's some alpha here, and you can also go around like this. This is the path beta. So maybe this is also like this. Yeah, you have these two paths, and they generate somehow the fundamental group of this. And this is our origin here. This is the x0. Yeah. Okay, this looks like this. And then, associated to this, one can define periods, omega 1. And this is the integral of this differential form omega over the alpha. And we can do the same with beta. And we have two periods. And these are complex numbers. Complex. And so we can look at the lattice, which is generated by these two periods. Yeah? So this looks now as follows. So you have here omega 1, omega 2. Yeah, and they generate a lattice. If you do this correctly, this looks like this, I hope. Yeah, and here you have a fundamental mesh of this lattice. Yeah, this sits inside C. And it turns out that you have a map from XC to C modulo this lattice. And this associates a point x here. You just take the integral from this fixed point x0 to x, and you integrate over omega. Yeah, and you have here now, you have a Riemann surface, and you take a path integral. Of course, this is not well defined in general. But in this case, we have somehow divided out the things where it's not well defined. Yeah, so if we somehow each homotopy class so if we take another path, then these two paths differ by something in this lattice. So modulo this lattice, this is a well-defined operation. And it turns out that this is actually an isomorphism here. And this is the way somehow these elliptic curves were classically studied by Abel, because if you make this explicit later, then these are exactly the elliptic integrals which Abel studied, yeah? So which have to do with the arc length of an ellipse, hence the name elliptic curves. Okay. So, but we have to go a little bit further. And we have to understand how such an elliptic curve looks like. And this is extremely classical, but it's worth recalling because it's also very beautiful. So Weierstrass has constructed the Weierstrass P function, which depends on this lattice. And this is 1 over z squared plus the sum over all lambda in the lattice, which are not 0. And then you take 1z minus lambda square minus 1 over lambda square. Yeah, and because of this term, this is actually in convergent series here. And you can take here the Taylor expansion of this, and then you get here a series where the coefficients are essentially the so-called Eisenstein series. So this is defined as the sum lambda in the lattice without 0, 1 over lambda to the 2k. This is called an Eisenstein series. And this Weierstrass P function, this is now defined on C modulo the lattice. This is a meromorphic function on this Riemann surface, and it satisfies the following differential equation. So quite easy to calculate. Square is 4p of z cube minus 60g4 p of z minus 140 g6 like this. So what does that tell us? So this tells us that each complex torus, each donut like this, is actually given by an algebraic equation. Yeah? X algebraic variety given by the equation, which I now call E for elliptic curve, y square equals 4x cubed minus ax minus b, this form. And it turns out, yeah, we started from an algebraic variety, but in fact, in the end, we know that there is a specific set of polynomial equations which describes them all. This is something which does not happen for higher genus. Yeah? You have no canonical form for curves of higher genus. But in this case, you have that. And it's this cubic equation which describes them all. So, and now we can do some arithmetic. Namely, if A and B happen to be rational, so if A and B are rational numbers, then we can speak about the solutions x of q, the rational solutions. Yeah? So, but even more is true here, and this is the reason why I took this detour, which is somehow maybe not the most natural thing to do. You see, the xc, this is C modulo lattice as a Riemann surface. And C has a group structure. This is the group under addition, and lambda is a subgroup. So this is really a group. Yeah? And it turns out, this is also an elementary thing about this Weierstrass P function, that this group structure is algebraic. Yeah? So moreover, xq is an algebraic group. And maybe I have briefly time to make another picture here, because this is something you see in many places. How does this group structure look like? It looks like this. So the real points of the elliptic curve look maybe like this. No. That's not a good picture, but the idea will become clear. These are the real points. And now I start with P1, P2, yeah, here. And then the group law goes as follows. I take the straight line through these points. And because this is a cubic equation, this intersects the curve in one further point, at least in the complex plane that's clear, but here it's also true. And then this is not the addition of these 2 points, but I have to reflect along the x-axis and get here the point which is then called P1 plus P2. Yeah, this is the result of addition. And you see, because if you give yourself the coordinates of these points by algebraic equations, yeah, or if there are algebraic numbers, these coordinates, then you have an algebraically defined straight line, and this straight line, and if you work that out, the polynomials which define this group law are actually algebraic. Yeah? So this is behind Abel's observation about these elliptic curves. So, and now we have the most important theorem due to Mordell. So XQ is then also a group, but it's more. It's a finitely generated abelian group. So this means XQ is of the form, it has some free part, z to the r, plus some torsion part. Yeah? So, and if we want to understand if XQ is infinite or not, we have to decide if this r is 0 or bigger than 0. Yeah? This is now the task. Yeah? So let's write that down. So this implies x of q is finite if and only if this r is 0. Okay. And now comes a completely weird thing. So the Birch-Swinnerton-Dyer conjecture is exactly about this r. But in a certain sense, you can think, what are the informations we have? What could encode somehow that r is 0 or not? And that's a very strange and difficult thing. And the idea, which is very classical and goes back to, I don't know, 2,000 years probably. So this is, we study, first of all, solutions of x over finite fields. So, I'm sorry, before I do this, I want to make a little example here. So, example, this fits in here. So we take the elliptic curve to be y squared equals 4x to the cube plus 20x. Yeah, and then one can show, so then the rank of, I write x and e here, this is not good. Rank of EQ, this is exactly 1. And a generator is, if I'm not mistaken here, given by the coordinates xy is equal to 1 over 4, 9 over 4. Yeah, this is the solution, and it's already not easy to see that this is really, this gives you a non-torsion point here, but you can do this. with these very easy curves. So it happens that the rank is greater than 0, and there are also many examples where the rank is 0. Okay, but what could determine somehow this dichotomy between rank 0 or rank bigger than 1, bigger equal 1? And for this, we have to study solutions over finite fields. And this is something which people in Diophantine geometry do all the time. If they cannot solve solutions over Q, they first solve things over finite fields, which have the advantage that there are only finitely many solutions. So you can also try simply certain solutions out, and if the field is not too big and your equations are small, then you can really do some computations here. So we assume now, this is not really a loss of generality, that A and B are in Z. Here we had A and B in Q. Yeah, but now let's suppose they're even in Z, like here. So the equation is now still the equation y squared equals 4x cubed minus ax minus b. And now we reduce this question modulo p. We fix any favorite prime you have, and you reduce modulo p. And then you look at pairs y comma x in this finite field, yeah, fp, which is z modulo pz. And you look if you have solutions in there. Yeah, because this is finite, this is maybe much easier. And as before, we define this. So this is just the pairs x and y in fp squared such that this solves this equation. Yeah? Y squared 4x cubed minus ax minus b. And then we have something which is technical. There's also a point in infinity which we don't see here. This is the reason why one should work with homogeneous equations. Yeah, but this point is always, this is the origin of the group law, and you don't see this here. Okay. This you can write down. And because here you have only finitely many entries, there can be also only finitely many solutions. And it's quite clear, if you don't have any solutions over fp, you also have no solutions somehow here of this in z. Yeah? And if you clear the denominators, you don't have any solutions in q. That's clear. Okay, so this is a testing ground. And now we consider the following number. Y1 defines it like this. I cannot explain here at the moment. So we take the number of solutions we have over that finite field for a prime p. So p is a prime number here. Prime number. Okay. And we don't consider the number of solutions, but this slightly twisted number here, AP. And then Hasse, in the 30s, I think, even in the 20s maybe, he proved the following fundamental estimate for these numbers. So if you want to know how they grow with p, then you know that they are always, the absolute value is always less or equal to of square root of p. Yeah? And this is a very interesting baby case, but this is another talk. If you study in general solutions of algebraic varieties over finite fields, then there are the famous Weil conjectures, and this is somehow the first instance of the Weyl conjecture, the first non-trivial instance here. Okay. But then it turns out, say we think that these solutions are interesting, we encode them in one function which knows them all. So for a complex number S, and for real part S bigger than 3/2, we consider the L series of the elliptic curve. And this is product over all P. And in fact, it's all P not dividing the discriminant of this equation, which I don't write down. These are only finitely many primes. And then you take 1 over 1 minus AP times P to the minus S plus P to the 1 minus 2S. Yeah? So it's an infinite product over all prime numbers. And it's strange why one defines this like this. You should think of the Riemann zeta function for an analog, but it's a little bit different, but it's in the same spirit. In any case, it's clear that it knows all these APs, and these AP know somehow the number of points over FP. And so this is the L function of E. And the Birch-Swinnerton-Dyer conjecture does something completely surprising. It relates this L function with this R, the number, the rank of this elliptic curve. So the fact if there are finite or infinite many solutions. So let's see how this works, should work. So first of all, one has to remark before I do anything. So it follows from work of Wiles on the Shimura-Tanyama conjecture that in fact, this L function has a holomorphic continuation to the whole complex plane. Yeah? This product only converges for real part S bigger than 3/2, but we can somehow extend it to a well-behaved analytic function on the complex plane. And now I can explain the Birch-Swinnerton-Dyer conjecture. So this was really found by Birch and Swinnerton-Dyer in the 60s, early 60s, I think maybe even in the late 50s. For computer experiments, somehow they wanted to find a relation between solutions over these finite fields and global solutions. And in the end, they made a conjecture. And the conjecture is as follows. BSD is the acronym we use in arithmetic geometry here. So E is an elliptic curve as before. Yeah? And then a miracle should happen. This R, which is the rank of EQ, this should be equal to the order of vanishing of this L function at S equals 1. Yeah? This is highly surprising because somehow it says that these solutions over finite fields, in a certain sense, they should know that there are solutions over rational fields, over the rational field. Yeah, and exactly they should know how many. Yeah, so the order of vanishing knows exactly the rank. Yeah, it's really very surprising and very strong. Yeah, so, and in particular, for our original question, this of course means, so EQ is finite if and only if the L function at 1 is non-zero. Yeah, it does not vanish. But in fact, much, much more should hold, and because this is somehow the starting point of a much, much, much more general conjecture which concerns all arithmetic varieties, all algebraic varieties defined over Q and their L functions. I want to write that as well, because there's also a conjecture for the leading term of this L function at s equals 1. So we divide out s minus 1 to the r. This is the order of vanishing. And if you think of the Taylor expansion of this holomorphic function in S, then this is the first non-vanishing term. And this has an expression, conjecturally, which involves almost all interesting arithmetic invariants of this elliptic curve. So there's the so-called period. There is the number of elements in the Tate-Shafarevich group. There is the regulator of the elliptic curve. I will not define anything which comes up here, but all these invariants are associated to the elliptic curve as an arithmetic object, and here you divide by the number of torsion points square. Yeah? This is the formula which should hold, and already the fact that all these strange numbers appear here, this is very surprising. And this is only part of a much more general conjecture where you have to define these invariants in a right way, involving all kinds of cohomology theories associated to this algebraic variety. Yeah, so this is the formula of Birch-Swinnerton-Dyer. And this is really a most amazing conjecture, especially we don't know if the so-called Tate-Shafarevich group is finite. Yeah, so this is somehow part of this conjecture. So I don't define this. This is only somehow something to marvel at, and there are analogs for number fields, and as I said, also for our other algebraic varieties, which we partly know, these conjectures. The general name is the equivariant Tamagawa number conjecture, and this is the most general conjecture we have. And this is really something very surprising. So we don't have any evidence, but we have completely general conjectures. Yeah? And this is something very typical for arithmetic geometry. And I always said, so if one of these conjectures fails, we can all go home, because then it's really not clear what we should do. We have a whole world built up, and we hope very much that this is true. Let me finally, 5 minutes, talk about results. So there are many results, and I apologize to all these people who are left out now. I will only mention the following. So the most important result still to date is the Gross-Sagi result from '83. And this says essentially that if the order of vanishing of the L function at 1 is less or equal 1, so either 0 or 1, then the rank of EQ is exactly the order of vanishing. Yeah? Okay. They don't say anything about this formula. This is difficult. But Kolyvagin somehow made some step in this direction. Kolyvagin, 88, I think, says, so if the L function does not vanish, then EQ is finite. This we knew somehow from here, but he has a new method of proof. And the Tejava-Revich group is also finite. And then from this result, one can, if one rearranges a little bit, these are transcendental numbers. So if you put them to the other side, then you get an algebraic number here. And then there should be an equality of algebraic numbers. And we can verify this equality for almost all p, so all primes up to finally many. So we know something about this. Okay? And then later, we get a different result. And for this, I have 2 minutes. Not so easy. I have only to explain that one should study this question also from an equivariant business. So if you have K over Q, a Galois extension, Galois with Galois group G, then one should consider not only the rational solutions, but one can consider somehow the solutions with values in the field K. And then I can also look at isotypical components, where, for example, chi is a representation of G, in some GLN-C homomorphism. And then I want to relate this to L values, etc. And what Kato proved is, so if chi is a homomorphism, it's a character, so into C star homomorphism, and the twisted L function is non-zero, then EK, the chi part, and the chi part of the Tejava-Revich group are finite. And somehow for this he developed further this method of Kolyvagin, which involves so-called Euler systems, and he could do this equivariantly and gets a new proof here, which is also different from Kolyvagin. And building on this, I will finish with the result, which was obtained independently by following people. So we have Bertolini, Darmon, and Rotger on the one hand, and independently myself and David Loeffler and Zerbes. And this is 14. And we prove the following. So if rho is irreducible two-dimensional representation, irreducible odd, then if the associated twisted L function does not vanish, then also the rho part and the rho part of the Tejava-Revich group are finite. Yeah? So Bertolini, Darmon, and Rotger they proved this, but they somehow pointed the general way how to do this, and in this paper there's an Euler system which also proves the finiteness of the Tate-Jaffe-Revich group. Thank you very much for your attention.
Thank you, Guido, for the nice talk. Are there questions? No questions? So maybe for the benefit of the students, maybe can you just say 2 words on the how this Tate-Jaffe-Revich group is defined? So
how this is defined.
Somehow
okay.
The main.
Unfortunately, this is quite difficult.
Yeah.
This is why I put this under the rug. But here's the definition. So everybody, I hope, knows what a principal homogeneous space under a Lie group is. Yeah, this is something where a Lie group acts in a faithful way on a space, and the quotient is the space. So you have P over X, say some manifold, and you have a Lie group G which acts on P, and it should act transitively, and if you divide out P by G, then you get X. So this is a homogeneous space. So the fibers of P look like G, but you have no origin signaled out. And this concept, of course, makes complete sense also in algebraic geometry. So you define the isomorphism classes of E principal bundles over Q. Yeah? And you call this H1 of Q E. Yeah? And it turns out that this is a group because G is abelian. This you can do, in fact, also in differential geometry. If you have a abelian principal homogeneous space, and you can define the tensor product of these two. And then this is the group. Yeah? And you can also consider this the same isomorphism classes over the local field QP. Yeah, I don't want to define that. And then you call this HQP of E. And the Tate-Jaffe-Revich group is simply the following. The Tate-Jaffe-Revich group, this is the kernel. So you consider these principal bundles over Q, and then you take the product over all primes P and take here the principal bundles over QP. Yeah, a principal bundle over Q gives also a principal bundle over QP. Yeah, and the kernel of this map, this is the Tate-Jaffe-Revich group. I don't know if this helps too much, but this is the definition.
Thank you. Are there questions? More questions?
I have a question.
Sure.
Isn't there any chance that people will prove something in rank 2? So all these results are in rank 1.
Rank 2 is really the most difficult thing we can think about. I mean, it's very strange that, I mean, these methods, they are extremely elaborated. So you need to invoke p-adic L functions. You need to invoke a lot of cohomology theories, like symptomic cohomology, etc. And this p-adic approach, for example, by Skinner and Orban, they can do also something in higher rank cases. And also in Kato's work, you can say something if the periodic L function somehow vanishes to a higher order. Yeah, because the periodic L function, this is essentially an element in the Iwasawa algebra and it controls the Selma group. And then it's quite clear if you have a main conjecture that some of the order of vanishing of the periodic L function and the size of the Selma group, they are related. This you know already since the work of Kato. But unfortunately, we don't know how the vanishing of the periodic L function is related to the vanishing of the complex L function. Yeah? And these periodic methods, somehow at the moment, we don't see how this could be related, which is certainly because we don't consider the right objects here. Yeah, so there is, if you have a higher rank case, you should not consider E. This is my opinion. You should consider something which is like a one motive, an extension of E by GMs. And for this, you should make periodic L functions, etc. And yeah, then maybe you have a chance to do something like this. But at the moment, the techniques are, the problem is everything here depends on the interpretation of the elliptic curve as, or the motive of elliptic curve as a weight to modular form. Yeah? And if you don't have that, you're lost. And for these higher objects, you don't have that, so there's no weight at the moment to do anything. But this is not only for the Birch-Swinnerton-Dyer conjecture, this is for all these L values conjecture. If the rank is 2, we don't know anything. Yeah, this is really, it's very sad. So all these students are now going home and work on that. You can become very famous, yeah, if you do that. It's certainly worth. But it will not be easy. You should better start today. Yeah?
Okay, if we don't have any question more, we thank the speaker again. And before we have the buffet,